It is my utmost pleasure to introduce another session of the ML Theory interest group here at Cohere Labs, officially now, not Cohere for AI anymore with the rebranding. And today we're really excited to welcome Jeremy Bernstein, who will be talking to us about the depths of first-order optimization. This is under our more general theme that we're starting now on optimization theory. So this is on the nice kickoff on a session, I believe, that ML Math had yesterday. So I think the video for that is online, should you want to, after this call, get more of a background in the deep mathematics, so you can follow that. But just a little bit about Jeremy for a bit of context. He is a postdoc at MIT, advised by Philip Isola. His goal is to uncover the computational and statistical laws of natural and artificial intelligence, and thereby design learning systems that are more efficient, more automatic, and more useful in practice. So personally, I'm very excited. I think there's very few people in the world that can give us this broad eye overview of all things optimizers. So we're delighted that you accepted our invitation. And yeah, the floor is yours. Take it away.
Thank you, Andre. Yeah, I'm really excited to be invited to speak. And my goal in making this talk, it was just to try to make the most use, make something that if someone had shown this to me at the beginning of my PhD, it would have been really useful to me. So that was kind of the mindset I had. Let's see. But yeah, recently there have been these training algorithms that have got a lot of attention, like Shampoo, Soap, and Muon. And there's like a basic desire to understand how they work. And if we understand how they work, then maybe, we could improve upon them, or there could be other benefits. What my perception of the kind of state of the field is that a lot of researchers, many researchers, they kind of have a pet theory. And if you're really into deep learning, then you may say something like everything should really be something called natural gradient descent. If you come from a more classical machine learning background, you may say something like, oh, everything should ultimately be mirror descent. If you come from pure math, you might say something like, if you want to do gradient descent, you need to have an inner product on your space. So these are all like ways to kind of rationalize and to think about optimization in an attempt to be more principled. But I don't think any of these perspectives are really the full story. And I just wanted to show you like an example of these points of view. So this was a tweet where a researcher was asking for resources on natural gradient descent. So they wanted to understand natural gradient descent better. And one of the replies was about how, according to a famous Russian optimization theorist, in a private conversation, they said that natural gradient descent is a bourgeois science, and really everything should be Newton's method. So it's just, I feel like this is an example of like where sometimes people are talking past each other, people are advocating for different methods. There's not really like a kind of global understanding or global consensus on how we should do things. So I wanted to think next a little bit about why are we in this situation? Why do we not really agree on these things? And one of the things is that deep learning is just not the most straightforward optimization problem. So we have a composite optimization where we compose like an error measure with a neural network. And then neural networks themselves are complicated functions. There's lots of tensors, they're high dimensional, and they have this compositional structure, just to name some of the issues. But essentially, it's not an easy optimization problem to understand. And then there's like one big research push which I've noticed, or maybe it's just that I pay a lot of attention to it. But one of the research pushes is on something called approximate second order methods. So the idea with this type of method is like there's some algorithm that you would really love to run, but it's just too expensive. So you would really love to run Newton's method, or you would really love to run natural gradient descent, or you would really love to run Avogadro. But because they're too expensive, we have to approximate them. and then there's various approximations that people consider, like ignoring how different layers in the network interact with each other, or Kronecker approximating gradients. And but the kind of general idea that people put forward is that there's some large matrix that you would really like to be able to compute to do your optimizer, but it's just too expensive. So let's take some kind of approximation to this matrix, like a block diagonal approximation, and further approximations on top of this, in order to try to get the benefits of this method, like the faster training, let's say, but without the computational overhead. But I want to challenge this perspective a little bit. So one of these approximate second order methods is called KFAC, which is supposed to be an approximation to natural gradient descent. But there have been 2 papers that I'm aware of that what they report is that they just run both algorithms. They run KFAC and they run natural gradient descent, and they find that KFAC actually works much better than that's what they report, at least. So somehow KFAC is a better optimizer than the thing that it's trying to approximate. Similarly, Shampoo is an optimizer, which is the way it was introduced was as an approximation to something called Adagrad, or full matrix Adagrad. Yet there's another recent paper which what they claim is that they ran both optimizers, and they just see that Shampoo is actually a better optimizer than the thing it's supposed to be approximating. So the point of, like, I can't conclusively say this is the case, but I'm just trying to sow some seeds of doubt that potentially some of these methods are not doing what they're advertised to be doing. That's what I'm trying to suggest. And so one of the goals for my talk, or that I wanted to get to, is this idea that first order optimization is a much deeper subject than we give it credit for. Oftentimes, if you think of a first order optimizer, you would think of just like regular gradient descent. But I actually think that we should, in some sense, think of these more advanced methods, things which people try to sometimes motivate as approximate second order methods. I think we should actually just think of them as first order optimizers. And that there's a lot of territory in first order optimization which you can explore, and these methods can be much more advanced than we sometimes give them credit for. And so before we go into it, I wanted to just tell you a little bit about the research that I've been doing, and sort of somehow reveal some of my biases, so you can also take what I say with a grain of salt. So I'm really into this idea of what I call metrizing neural networks, by which I mean assigning distance measures to all the spaces inside a neural network and trying to find meaningful distance measures. And I'm hoping that this is going to help in a variety of different areas. One of them is optimization, but also with systems things like numerics, potentially enabling us to certify properties of neural networks, and potentially other advantages. One of the optimization areas that got a lot of attention recently is the Muon optimizer, which I was involved in, and I wrote a blog post on the theoretical background of this algorithm. And it's an optimizer which is supposedly faster and more scalable, or more intrinsically scalable, giving better learning rate transfer properties somehow by design, as compared to Adam, let's say. And then on a broader point of view, I'm working on something called modular, which it's built around this idea of thinking of neural networks kind of like a Lego set, where we have the little layers of the little Lego pieces, and then we put the pieces together to build the neural network. But all the pieces have theoretical statements attached to them, and then as we build the network, we also build up a kind of theoretical understanding of the network and at the same time. And it's supposed to try to bring together these somewhat disparate areas of deep learning theory, optimization theory, and programming languages. So this is the broader project that I'm really excited about. And then the final thing before we get into things is that the research I've been doing is all the result of like really amazing collaborations and really amazing collaborators. So like early in my PhD, I started thinking about distance functions and distance measures for neural networks. We made a lot of progress in this project in the modular norm. So I really want to emphasize Tim, who I guess doesn't tweet as much as I do, but is like a lot of the ideas we develop like really closely with each other. And Tim is like amazing pure mathematician, a fantastic collaborator. He's an old friend. I also want to emphasize Philip, who's my postdoc advisor, who's just given me a tremendous amount of freedom and like was also not the kind of postdoc advisor who tried to like stamp his name on all of my work, but probably should have done. But like I'm incredibly grateful to have been able to work with Philip. He's a really great advisor and a really great person. And then in Muon, I just want to emphasize Kala and also these great kind of open source collaborators. So yeah, that's everything I wanted to say. But yeah, I've really been fortunate to have really amazing collaborators. So at this point in the talk, I felt like the most useful thing I could do is kind of do like a survey of the different ways in which people think about optimization to try to build some kind of like basically a background and context with which we can try to place things. So just to set up some notation, let's talk about a loss function L, and we'll always think about having a set of parameters in Rn, or the weights are an n-dimensional vector of weights, and the loss itself is a real number. In first order optimization, we will have a gradient, which I'll just use G as a shorthand for the gradient of the loss. And a very simple example of a first order optimizer would be like vanilla gradient descent. And in second order optimization, usually we would have like a gradient and a Hessian. And obviously the Hessian is a matrix. And we would somehow use the second derivatives as well as the first derivatives to inform how we do optimization. So maybe the simplest example is Newton's method, where we invert the Hessian and use it to kind of reshape the optimization step. Okay, the next thing I want to show you is like how to derive an optimization algorithm in a very broad terms. This is going to be useful because it's going to give us a pattern that we're going to see repeated over and over again in lots of different contexts. So what I would say is step one for deriving an optimizer is to do a Taylor approximation of your loss function. Step two, like, so for the first order optimization, it would be a first order Taylor approximation. Step two is you then like model the higher order terms. So you say, hey, this is how I think the higher order terms behave. Your model may not be correct, but you come up with some model. And then you minimize the model to update the weights. So it's basically the optimization is about computing a local approximation, like a local Taylor approximation, and then expressing some kind of belief about how the function behaves as you move away from that point, and then minimizing the model. And then you just repeat that process over and over again. This is like a formal way of deriving optimization algorithms. And just to show you like the simplest example of this like design pattern, to get the most vanilla form of gradient descent, we would Taylor approximate our loss function up to first order, model the higher order terms with a Euclidean norm penalty, so a kind of quadratic model, and then minimize this quadratic. And this is just to show you that changing, I wrote a parameter lambda here that controls the strength of the quadratic model, and varying that parameter just sort of varies the sharpness of the quadratic and would lead to taking bigger or smaller steps. And then the final thing that we do is we minimize the model. So to do that, we just differentiate the right-hand side and set it to 0. So we differentiate with respect to delta W, which is our weight update, set the derivative to 0, and then solve for delta W. And in this case, because we have a quadratic model, like an isotropic quadratic model, we just get the most vanilla form of gradient descent. But you could imagine putting different models here and getting different optimization algorithms as a result. So the big question is, like, in practice, how should we model the higher order terms in the loss function? And there's a lot of freedom because you can just come up with whatever model you want and you're allowed to do that. And people have, in fact, done that over the years. And just to show you, just to like throw out some names of some techniques, like using different mathematical structures to model the unknown behavior of the loss as you move away from your approximation. Different mathematical structures give you different optimization algorithms. So one structure could be an inner product. Another thing people talk about is a Bregman divergence. You could actually use the Hessian matrix to build an actual second order model. You could use a non-Euclidean norm. And all of these different structures give us different ways of doing optimization. By the way, if feel free to ask questions, or otherwise I'll just keep going.
I think there's no questions in the chat at the moment. I have 3 questions, but I'll say them to the end just to spur the discussion after the talk. So I think you should just keep going.
Sounds good. So I got worried. Partly I was worried that it's going to be a little dry. So I made this map of optimization using ChatGPT to help guide us. So I'm going to start off by talking about just straight up what I regard as straight up first order methods. So one approach to first order optimization is called majorization minimization. So this would be the idea that we take the Taylor series of our loss function and just actually find an upper bound, really produce an upper bound on the second order and higher terms. And we'll call that upper bound a majorization. And then we would minimize it to get our optimization step. So advantage of this technique is that if you minimize a majorization, it's guaranteed to reduce the loss. But some of the disadvantages of this approach, one is it may be difficult to produce a majorization because you have to figure it out, and it may be difficult to figure it out. And also, it may be a slightly too conservative or too pessimistic approach to really have a true upper bound on your loss, because sometimes it may be okay to take steps that are bad as long as overall you're doing well, and there's it may be too conservative to have a method which is really guaranteed to make good progress at every step. This is one that we just already talked about. So vanilla gradient descent would be the idea that we model the higher order terms in the Taylor expansion using a Euclidean norm. And the parameter lambda could be something like the max eigenvalue of the Hessian, in which case this would really be an upper bound on the Taylor expansion, actually. So there are conditions under which this would actually be a majorization. And we then minimize this, and we get the vanilla gradient descent algorithm. The advantage is simple. But you may not know, disadvantage, you may not know what the max eigenvalue of the Hessian is. It may actually vary. It may change throughout the space, which would complicate this procedure. The Euclidean norm is isotropic, meaning it's kind of the same penalty in all directions in the space, but that may be a bad fit for your loss function. The next one I wanted to talk about is gradient descent on an inner product space. So this is the idea that we have a positive definite matrix A, such that this purple box gives us a good model of the higher order terms. So an inner product can always be obtained from a positive definite matrix. Maybe it also has to be symmetric, I forget. And then this expression is minimized by inverting the matrix and multiplying it by the gradient. And so this one is like a pro or a con, depending on your point of view, but it gives you the freedom to pick a different inner product, and you can use that freedom. But the disadvantage of this perspective is you may not know what a good inner product is. So then it's a disadvantage because it doesn't actually tell you what to do. So that's going to be true of a lot of the techniques we look at, is like they give you freedom, but you may not actually know how to use that freedom, or that, there may not be a good way to use the freedom. Similar is there's another approach which is called, or which I will call, steepest descent under a non-Euclidean norm, which is basically the same as vanilla gradient descent, but we generalize the norm, and then lambda should be some kind of generalized max eigenvalue of the Hessian. And it turns out that you can express the minimizer of this thing the following way, as like the product of the dual norm of the gradient with a maximization subproblem over the norm ball. That's just like an exercise to show that. And again, like this could be a good or a bad method because it just gives you more freedom. Like now you have freedom to find different norms, and maybe some norms will give you a better way to model the loss than other norms. So that's something to consider. And this lambda parameter, so the generalized max eigenvalue, you may still not know what it is. It may vary in the space. Like who knows how that would behave. I think this is the last of the first order methods. So mirror descent. This is one I did grad school at Caltech, and everyone just constantly told me that all first order optimization should be mirror descent. Like the professor, a lot of people really believe that mirror descent is like the end game of all first order optimization, but I actually don't think that that's true. That mirror descent says to pick your favorite convex function on the weight space, extract the nonlinear part, so like remove the linearization from the function. So you can do that for pretty much any function. Okay. And then you just roughly use the nonlinear part of the convex function as a model for the nonlinear part of the actual loss. To me, this is the best explanation of what mirror descent is. I think it's actually controversial. Like someone tried to tell me this is not mirror descent, and they said this is like actually a special thing that Nesterov came up with only recently, but I don't understand that perspective. Okay. But I put a reference at the bottom of the slide in case you want to read more about that. But again, this is either a pro or a con. It just gives you the flexibility to choose a convex function. And you may not know how to choose a good convex function. Like for a neural network, it's not obvious what convex function you should choose, which I think is why people have struggled to productively apply mirror descent to deep learning. Okay. See those things, I think of them as first order methods. And the reason I think of them as first order methods is because they use the actual gradient, and then they use some kind of analytical model of the higher order terms. And I would think of a second order method as something that actually uses actually uses the Hessian matrix. So classic second order method is Newton's method. And this is where we just drop the third order and higher terms in the Taylor expansion and just minimize the second order approximation to the loss. And you can do that, and the result is that you should invert the Hessian and multiply it by the gradient. So a pro of this approach is that you actually use the actual second order information, which seems like that could be good. Negative is that nothing about minimizing the actual second order approximation. Sorry, we've not actually minimized it. We just found an extreme point. And an extremal point could be a stationary point, or it could also be a local max. So like Newton's method may not actually minimize your loss, it may actually maximize it depending on where you are. And then the other thing is like, the Hessian may not be invertible, or it could have really tiny eigenvalues, which would lead to you taking really giant steps. And so it's somehow like a kind of, I was thinking a good way to put this is it's a kind of self-defeating method, because it can lead you to take giant steps which are so large that the approximation that it's based on no longer holds, which is like a really bad property of an optimization theory, that it kind of defeats itself. Actually, a lot of the methods people propose have that property, that they kind of defeat their own approximation, and that's really bad. Another problem with Newton's method is it may be too expensive to compute the Hessian matrix. But thankfully, Nesterov figured out a way to kind of fix the problems with Newton's method, and it's called the cubic regularized Newton method. And basically, the idea is that you add a cubic penalty to the second order approximation, and then you minimize this cubic model of the loss. So intuitively, the cubic penalty should fix the types of problems where you like run away too far. Like it's still even if the Hessian is singular, like minimizing the cubic objective function is still like a well-defined thing. So it just fixes, like, in other words, it's doing what we said that you should do all along. You should like Taylor approximate the loss and then have a model of how the function behaves as you move away from the Taylor approximation. So this cubic method is actually doing that. So it will actually minimize your function. It won't converge to local maxes or stationary points. And it's well behaved even when the Hessian is singular. The downside is that the Hessian, it's still an expensive object. You may not be able to compute it, fit it in memory, invert it, and so on. So those are the ones which I wanted to call second order methods. And then the next part is this middle ground, approximate second order methods. So what are they? So the thing I wanted to emphasize here is that in deep learning, we have this composite optimization problem where we compose an error measure with a neural network. Because we have a composition, we can apply the chain rule for the gradient, and we can split the gradient into two pieces. And then we can take another derivative again to compute the Hessian. And because the gradient is a product, the Hessian, we can apply the product rule. And we get two pieces of the Hessian. And this is oftentimes referred to as the Gauss-Newton decomposition of the Hessian. But it's basically an expression for the second derivative of a composite. You get two pieces. And so many of the approximate second order methods start with this this is the starting point. By the way, if people have I just realized that I have no sense if anyone's even following or finding it interesting. So if you do have questions, feel free to ask.
So far, there's no questions in the chat, but let me maybe ask one of my questions. I was going to ask it at the beginning. When you were talking about that, in certain papers, the approximations of certain moments, of certain optimization algorithms become more superior, at least in the experimental benchmarks within the paper, of the method that they're trying to approximate or developing an approximation of. Why do you think this gap is the case? Is there some inherent regularization property in the approximation that maybe lends itself to prevent overfitting, or is this just a poorly designed, set of results in an experimental paper where because of maybe the computational complexity that the full method prevents you from exploring, that you actually haven't sought out the true result where you would find that the full method is better than the other?
Yeah. I'm just going to tell you what my suspicion is, and I'm going to be honest that there's a few different things. One is I I haven't read those papers as closely as I should have done to make a confident statement. So I just want to preface, but I think the most, like, my genuine opinion is that the flavor of some of those papers is let's take this method and make a series of very extreme approximations, and we're basically no longer confident that the supposed approximate method actually bears any relation to the thing that it's supposed to approximate. This is my suspicion. Like, I'm not gonna say flat out that that's the case, because I could be wrong, but like, just taking the Shampoo paper as an example, like, I'm pretty suspicious of the theoretical arguments in the Shampoo paper, like the original one. I'm like, there's been multiple papers since the original one, so I can't. But like, it may be the case that the method that they're just trying to approximate is actually not a good idea, but the approximate method that they come up with actually is a really good idea. And it's not, the reason it's a good idea is not because it's approximating full matrix Adagrad, let's say. Just, that's my, like, that's honest. I honestly think that's the most useful thing I can say, is that, like, it's just like my honest belief is that, like, the original Shampoo paper, like let me put it this way, like, full matrix Adagrad is not a good idea of a training algorithm for a neural network. That's probably like the most blunt thing I could say, but with the caveat that I may be wrong. So I'm just saying that because it's my honest belief, and I think it's useful for me to say that, but I could be wrong.
And then Ed has put up their hand, so feel free to unmute yourself, and the floor is yours.
Yeah, hi. When you're talking about the cubic regularized Newton method, you might have already said this, but can this be viewed as like another kind of majorization, minimization sort of thing? But now we've also got an exact second order term, and we're sort of doing a penalty on the third.
Yes, exactly. So the way they present it in the paper is exactly that way. It's like, let's suppose you can build cubic majorizations of your objective function. Like, what would happen?
Sure. Okay, cool.
Exactly.
Thanks.
Other than this, there's no questions in the chat. There's just a remark from Tim that says, locally quadratic convergence of Newton's method is only guaranteed for strongly convex functions with Lipschitz Hessian. See example, Bach's learning theory book. So I guess, I don't know whether you have anything to add to this, or it's more just a comment to the general audience.
No, that's a thanks, Tim. Yeah, and maybe something I could add is that I oftentimes I feel like the perspectives I have are slightly blurrier and slightly imprecise for the taste of like a hardcore optimization theory person, and so that's why I feel like I don't necessarily have any collaborators who are like hardcore optimization theory people and so on. I think there's actually a lot of value in slightly imprecise takes, which are kind of diffusing towards the truth in a way, which is what I regard. Okay, anyway, that's a random thought. I didn't know why that came into my head. But I really regard the science of these systems as a kind of diffusion process where we're gradually like getting closer and closer to the truth, but we're never quite there. Anyway. This is just to say composite optimization. We have a decomposition of the Hessian. Gauss-Newton method tells you to ignore one of the terms. It just says one of the terms involves the second derivative of the neural net. Let's ignore that term. And let's also suppose that we have square loss, in which case the Hessian of the error measure is just the identity. Let's use this to build a model of the Hessian and then minimize it. And we get this algorithm, which is called the Gauss-Newton method. Like one of the reasons people like this method is that it does incorporate information from the Jacobian. That is information in the Jacobian of the neural network, and the method somehow exploits that. But downsides are, again, you don't actually want to compute Jacobians because it's expensive to compute. And again, it's what I regard like as a self-defeating method. The method can lead you to take steps which are so big that the approximation that it relies on no longer holds. So it can be that's a poor optimization theory in a sense, because it leads the algorithm takes steps which invalidate its own approximation. So that's a criticism of the method. Generalized Gauss-Newton just says let's not assume that we're dealing with square loss, and let's just keep that extra term. Okay. Natural gradient descent. This one says pick your favorite distance function on the outputs of the neural nets. You get to pick whichever one you just your favorite one, and then use that as a model of the higher order terms in the loss. And the rationale is like distance in function space is surely what ultimately matters. So let's just use that as a model. And then they do an extra step, which is to get like a second order approximation, or you can think of this as actually a Gauss-Newton approximation of your distance function on function space, and in order to sort of pull it back to the weight space. And then minimize that model. And if you flick back and forth, you realize it's essentially the same thing as the Gauss-Newton method, just you've replaced the loss function with your distance function of choice. So it's closely related to the Gauss-Newton method. And so that freedom, it could be a pro or it could be a con, depending on if you have a good idea of how to use the freedom. And it's also like has this self-defeating property where it can lead the updates to be so big as to invalidate the approximation. Okay, so that's the end of like the tour through the land of optimization. But what I wanted to say at this point is that like those are the ways to me which feel like the most popular ways for thinking about neural network optimization. But there's other ways. In particular, there's one other way which we think is a really good idea. And so I wanted to phrase it as like there's this place on the map of first order methods that not a lot of people know about, but it's a really great place, and it's been really underexplored. And so let's try to build this, what I call a new optimization model. So the idea is that we're going to do 3 steps. So the first step is to use the Gauss-Newton decomposition of the Hessian. The second step is to apply Cauchy-Schwarz inequality and apply operator norm upper bound to sort of separate out the pieces in the Gauss-Newton decomposition. And then step 3 is to suppose that your neural network is both a Lipschitz function and a smooth function in its weight space. That's a really complicated thing to think about. But for now, let's just suppose that that's true. If it's true, we can build a optimization model of the second order terms in terms of a norm on the weight space. So it's a way to kind of convert the Gauss-Newton decomposition into a statement about norms of weight updates that works in 3 steps. And I just want to emphasize that it's like a different argument to the one that underlies natural gradient descent. It's a different argument to, let's say, those other things that we talked about, but it's a way to connect the optimization landscape to things that involve norms on the weight space. But so the key thing here, like the non-trivial thing, is like, what does it mean for a neural network to be alpha Lipschitz and beta smooth? Like, how could we produce such statements for a neural network? And it turns out there is a way to do it, which is something that I work really closely. It's this paper about the modular norm, and it's the project with Tim Large, and that's kind of what we did. So like the way we thought about this is we thought really carefully about the global structure of deep learning, basically. So we've got this structure where we have a bunch of weight matrices and we update them using update matrices. And then these weight updates induce changes to the network output and they induce changes to the loss. But if you do something like natural gradient descent, you actually forget the fact that there's matrices. You're sort of agnostic to the structure of the weight space, but the weight space has a lot of structure based on the fact that it's built out of tensors, it's compositional and so on. And you're not thinking about that if you're using natural gradient descent deeply. You're just relying on autodiff to compute Jacobians for you. But the idea here is, what if we think in a really detailed way about the actual structure of the weight space and like basically do more analysis than what you would do in natural gradient descent? That's the high level idea. And the way we thought about this is that the local structure of individual layers is easier to think about. And I can make statements like if I take a linear layer and I update its weight so that the outputs change, I can produce Lipschitz statements for a single layer very easily. And they're going to involve some kind of operator norm on the weight space. So this is a bound that relates the change in function to the change in weights and the size of the input. So I can produce Lipschitz statements for individual layers. And then the smart thing about the modular norm, which honestly is like, Tim figured out how to do this, not me. But the smart thing is that you can then compile these local statements into global Lipschitz statements. So the global weight space is this Cartesian product of all the different matrix spaces. And for each layer, we, in a sensible way, assign a norm to the layer and a scalar coefficient for each layer. And then we build this global norm as a kind of max of the different layers. And you think of the norm, each layer's individual norm is somehow well matched to the structure of that layer. And then the scalar coefficient S estimates, like, if I change that layer, how much does that individual layer influence the overall function? And then we kind of aggregate all the norms using a max. And then the cool thing is that under certain conditions, which you have to be careful about, that you can actually prove that the network is Lipschitz and Lipschitz smooth with respect to this thing that we call the modular norm. And so that allows us to build our optimization model. So like the optimization model, which I said is a new way of doing it, or it's a way that's at least very underexplored, is now workable because we've actually built a way to produce Lipschitz statements for neural networks in their weight space. And so if you recall, like towards the beginning of the talk, I was telling you about steepest descent in norm spaces. Well, now that we've built a norm for a neural network, we can just apply this framework. And for the modular norm, because it's a max over layers, the descent direction decouples over layers and can be solved separately for each layer. And it involves solving a analytical maximization problem for each layer. And then the question becomes, what, by the way, I'll just try to finish in the next like 2 or 3 minutes because I realize time is running out. The big question just becomes, what norms should we assign to individual layers in the network? And if you assign a vector L1 norm, sorry, there's a mistake on this slide. That should be the L infinity norm. But if you assign the vector L infinity norm, you get this sign descent algorithm. And if you assign the matrix spectral norm, you get this spectral descent algorithm. And the thing which Laker and I pointed out in this workshop paper is that, like, if you disable EMA and Adam, it's equivalent to sign descent. And if you disable EMA and Shampoo, it's equivalent to the spectral descent algorithm. And it's just like provides a direct and quite simple way to understand these methods, which people use as just like steepest descent under a norm plus some kind of momentum or plus some kind of smoothing. And so this is like this attempt to try to tie together these things which people have been doing. Like, no, I don't think that Shampoo is an approximation to full matrix Adagrad. I literally just think it's like steepest descent under the spectral norm plus some kind of smoothing. And this is, it's important to mention that someone called Thomas Flynn and then researchers Carlson et al., they had this idea about these norm-based algorithms like a really long time ago, and like everyone kind of just ignored, that's the feeling I have. Like, for instance, the paper from Thomas Flynn has like one citation. It's like, in my opinion, it's like a really amazing paper that a lot of people should read. Okay. Muon is kind of like steepest descent under the spectral norm with an efficient Newton-Schultz iteration for computing the kind of spectral mapping. If you use a more refined choice of norms, you can get automatic learning rate transfer. So this is this meme, which I'm trying to say is that mu-p and muon are really like, you should view them as actually the same thing or approximations to the same thing. That's how I think of them. And I think it's like the kind of end game potentially for thinking about them is just approximations to this single maximization procedure under the spectral norm. And then this is the horizons, which I am happy to talk more about. Essentially, for me, like this modular project, the attempt to build this optimization theory into an actual programming language. And then there's like various other avenues that I'm really interested in that I think can be built on top of these kinds of ideas. But I'll probably finish and just ask if anyone has questions. So I'd love to discuss more. So yeah, thank you for listening to the talk.